We'll take a look at a few more examples now. So problem number 1, find the z-value that corresponds to the shaded area. All right, so we're looking for a missing z-score. So again, I just like to put a little question mark there. So if we're looking for a z-score and they give me the shaded area, in this case, what's shaded is the area to the right of that z-score. And it is 0.8615, so 0.8615. And now we know that what I need is area left of the z-score, if we would like to use inverse norm. So 1 minus the area to the right will give us the area to its left. So we apply the rule of complements. That area is 0.1385. And then we're able to enter that area left into our inverse norm function. And then as always, we'll check if our answer makes sense visually, but we'll go to our inverse norm, 0.1385. And I'll continue to round to 2 decimal places, so negative 1.09. So in terms of whether that answer makes sense, we're just seeing if relative to the mean 0, it's a negative z-score making sense? Yes, because we know our answer is to the left of center. So to the left of the mean. So just always making sure visually things are making sense. All right, number 2. Find the z-value such that 20% of z-scores lie to its left. In other words, find the 20th percentile z-value. All right, so we'll use this as an opportunity to discuss percentiles, but first, let's get this given information. So find the z-value such that 20% of z-scores lie to its left. So they're giving you the area to the left. They'd like that to be 20%. All right, or 0.20. All right, so these are the easy cases because there is no work to do. If you know the area left, that's exactly what you need to enter into inverse norm. So you just go directly to inverse norm. So it's important to see the difference between these two questions. And as long as you remember you need area left, you should be good. All right, let's see if that makes sense on our picture. So we'll inverse norm 0.20, and that's a negative 0.84. Okay, so let's discuss this answer relative to the definition of percentile. All right, so I'm going to label my axis here. So we're looking at z-scores. We know the mean is 0. And we know that for these symmetric distributions, that would be the 50th percentile. So 50th percentile would be in the middle because 50% of data is to the left of it. And also 50% then would be to the right of it. And then it says that the value we were looking for would be the 20th percentile. So the 20th percentile will be to the left of the 50th percentile. And it's looking good here because our answer is to the left of the mean, negative 0.84. So that negative z-score makes sense. And then we are going to be interpreting these percentiles as well. So let me add some information to the picture. So we just found the z-score that puts 20% of z-scores to the left of it, which means that to the right of the 20th percentile, so that area to the right of it, I'm going to just switch colors to shade it. So all this area to the right of it will be the complement of the left of it. So if 20% is to the left, the other 80% is to the right. Okay, And we'll continue and revisit percentiles, but that's our answer then for that one. All right. Number 3. Okay, so for the standard normal distribution, find the z-value that corresponds to the 90th percentile. And then I did go ahead and repeat the definition of percentile value. All right, the percentage of data values that are less than the value. So let's go ahead and label our axis here. Z, 0's in the center. That's the 50th percentile. We're looking for the 90th percentile. So that would be somewhere to the right of center. And I'm going to shade the definition. So the definition of percentile, it's the percentage of data to the left of that value. So whatever that percentile value is, we know that 90% of z-scores need to be to the left of it. So that picture is the definition of the 90th percentile. All right. So let me go ahead and shade the area to the right of it as well. I'm just going to switch colors here. So if 90% of z-scores are left of P90, then the other 10%. So the complement of that, the area to the right then would be the other 10% of z-scores. All right, so let's find that z-score. So that z-score, we're looking for the z-score that represents the 90th percentile. And we know that the area left of that number is 90% or 0.90. So we can just inverse norm that area to the left of it. Okay. And that is positive 1.28. And a positive number makes sense because P90 is to the right of 0. Okay, so let's go ahead and do 2 interpretations then of that value. So approximately, what percentage of z values are less than that value? So 90%. So approximately 90% of z-scores or z values are less than z equals 1.28. And that would mean the complement percentage, 10% of z-scores or z values are greater than z equals 1.28. All right. So we're going to do one more case, but it really isn't exactly a new case. We're still going to apply what we've done in the other cases. And we're going to be seeing this type of example throughout the semester, where we start talking about the middle of the bell curve as opposed to the tails. So the middle of a bell curve as opposed to the tails. So left tail, right tail. And you'll see why all of this is important in the future. So for now, we'll just kind of take a look at an example, and this is the one we'll look at. So it says find the 2 z values such that 95% of the middle area is bounded by them. So the middle 95%, I'm just going to write that as a percent here. So 95% of the data. So back in chapter 3, we talked a little bit informally about this number and said that data that was part of the middle 95% would still be considered typical. And when we start getting more extreme than that, we start to say values are atypical or unusual. So in the world of statistics, this 95% as a proportion or probability comes up a lot, which we'll see. But for now, we shall move forward and look for the z values that make this picture happen. So just to be able to call the z-score something over here, I called it the z-score to the left of center and the z-score to the right of center. So we're looking for those 2 z-scores. We're going to learn more formal notation for those later. All right. So let's go through the decimal version though. So 95% is 0.95. And we're going to do a little bit of notating here. What is the area in the two tails? So these two together. So the idea is the whole bell, I'm just going to write this at the top again. So the whole bell area would equal 1. So 1 or 100%, but we'll stay with decimals. The whole bell has to add up to be an area of 1. So in order to find out what's in the tails, we do the rule of complements. So if you take 1 minus that middle area, I'll just write it in English. So if you take 1 and subtract the middle, that gives you what's left over in your tails. So that will be 0.05 or 5%. So if I want to know how much is in each tail separately, in one tail alone, I just take that two tail area, that 0.05, and divide by 2. So that'll be 0.025. Okay, so on the left tail then, that tail, that area to the left of the z-score on the left, we know now is 0.025. So let me just write that. So that area left is 0.025. So the other tail, the right tail, so that area to the right of the z-score on the right is 0.025. So we'll see here, did we do it correctly? If I add up all those areas, do I get 1? So if we take 0.025 plus 0.95 plus 0.025, you will indeed get 1. So we're just breaking up the bell into the middle and the two tails. Okay. So if I want to know the z-score on the left, we know the area to its left, and that means you can just go straight to inverse norm. So I'm going to do that one first. So for the z-score on the left, because we know the area to the left of it, we can inverse norm. But let's talk about the z-score on the right. So for the z-score on the right, I know the area to its right, but remember that to do inverse norm, we need the area to its left. So all that area to the left of it. So now we're back to the cases we've already talked about. So if we know the area to the right of it and we want to know the area left, it's always 1 minus the area to the right. So if we take 1 minus 0.025, that will be 0.975. That would be the area to the left of this z-score. All right, so all this sort of geometry of a bell is going to be important, just seeing how you can break things into different areas. And we're picking the area that's going to help us find the z-score. And in this case, then for inverse norm, if I want to know that z-score on the right, I would be inverse norming the area to its left. So if you can just always remember, you inverse norm the area left of what you're looking for, that will be priceless. So for this one, we inverse norm that. For this one, we inverse norm that. And then let's go ahead and type these in. All right, so let me do the first one. So if I inverse norm 0.025, that's negative, and I'll round to 2 decimal places. We saw this number a little bit earlier in the notes, actually, negative 1.96. So almost negative 2. So from center, it's almost 2 standard deviations away. And then if you inverse norm 0.975, So this may not be surprising based on the symmetry of the graph, but that comes out to be positive 1.96. So numerically, the size of the number is the same, but one is a negative value and one is positive, because remember, as always, the mean mu in the center there is 0 when we're talking about z-scores. All right, so one positive, one negative. All right, so we're going to be dealing with that picture quite a bit later in the next chapter. But that just kind of is a good summary of remembering that if you want to find a z-score, you inverse norm the area left of the z-score.